students! How's your day? I hope you're doing just fine. Are you ready to learn math with me? Let's go! Today we are going to learn about orthogonal basis. So, basically, an orthogonal basis for a subspace W of real number is a basis for W that is also an orthogonal set. Theorem for orthogonal set says that all vectors in an orthogonal set are linearly independent. For example, consider the vectors u and v given by u is 1, -2, v is 6, 3, and that is the graph of these two vectors. In general, for vectors in real number, we use the term orthogonal rather than perpendicular. Specifically, if u and v are vectors in real number, we can say that both vectors are orthogonal if u dot v equals to 0. Theorem for orthogonal basis is let u1 until up be an orthogonal basis for a subspace W of real number. For each y in W, the weights in the linear combination are given by. Then, for the general form, we can simplify it until the equation below. To prove the theorem, as in preceding proof, the orthogonality of u1 until up shows equation below. Since u1 dot u1 is not 0, the equation above can be solved for c1 to find cj for j equals to 2 until p. Compute y dot uj and solve for cj.
Now, I will show you the first example for orthogonal basis. Okay, for the first question, show that vector u1 and vector u2 is orthogonal basis for real number 2. Then, express vector x as linear combination. So, based on the orthogonal basis theorem, orthogonal basis can form linear combination. Okay, so we can go through to the question. Okay, so for vector u, the vector is 2 and -3. For vector u2, 6, 4, and for vector x is 9, -7. So the first step of doing this question is to show that orthogonal basis is linear combination. The first step is we must show first step is to show that the vector is orthogonal set u1 dot u2 is equals to 0. So for this question, our u1 is 2, -3 times with 6, 4. So it will become 2 times 6 plus -3 times 4. We can get the answer is 0. For the second step, to show vector u1 and vector u2 is linear combination. To show vector u1 and u2 is linear combination. Okay, by using theorem of orthogonal basis, that orthogonal basis can form linear combination using this formula. X equals to x dot u1 over u1 dot u1. The variable is u1, okay? Plus with x dot u2 over u2 dot u2. The variable is u2. So all of this is vector. Alright, then we can insert this variable with the matrices. Alright, so we can get except for this one, we do not replace it with the matrices. Okay, so plus okay, so here is, so after further calculation, we can get 39 over 13 u1 plus 26 over 52 u2. Okay, so we can relate this answer with general form of linear combination, which are x equals to a1 u1 plus a2 u2. Okay, so it is in the same form. So we can simplify the answer. So we can get 3u1 plus 1 over 2 u2. u2. Right? Then we replace u1 and u2 with their matrices. So we can get 3, 2, negative 3 plus 1 over 2, 6, 4. So this is our answer. So basically, this is the form of linear combination. So it is proven that vector u1. Alright, now for the second example. Show that vector u1, u2 and u3 is orthogonal basis for R3 because we have 3 vector. Alright, then express X as linear combination. Okay, so the step for, okay, so first step is we just use the same formula to show it is orthogonal set. So u1 times u2 equals to 0. So this is only for 2 vectors, and if we have 3 vectors, we have to show that each vector to each other is equals to 0. So for the second one is u1, u3 is equals to 0, and lastly u2, u3 is equals to 0. So if we can prove that all of this vector is equals to 0, so we can show that it is an orthogonal set. Okay, so for u1 dot u2, is, so we can get the answer is 0. So for the next one is, so we can conclude that okay, for the next step, so we use the same formula from the theorem, which is x okay, we replace it with the matrices. Okay. Okay. So after we calculate, we can get so if we simplify, we can get 5 over 2 u1 plus 3 over 2 u2 plus 2 u3. So we replace it with the matrices. 5 over 2 1 0 1 plus 3 over 2 negative 1 4 1, and lastly 2 2 1 negative 2. So we already express it in linear combination. Okay, so we continue with example 3. So basically, the question for orthogonal basis is almost the same for all question. So basically, we have to show that whether this vector is orthogonal basis, and then we express it as linear combination. So first thing first, we use the same formula to determine whether this vector is orthogonal set, right? So because we have 3 vectors, so we have to do it 3 times. So all of this must equals to 0 to show that this vector is an orthogonal set. Okay, so firstly we show that u1 dot u2 get negative 2, which is not equals to 0. Okay, so from here we can say that this vector is not an orthogonal set, but we can check further. For the next one is u1 u3 beget 2, also not equals to 0. Okay, so next is u2 u3 0. Only U2 times U3 get the answer is 0. So the condition to show that the vector is orthogonal said that we must prove that all of this is equals to 0. So we only get U2, U3 is equals to 0. Okay, we can conclude that U1, U2 is not equals to 0. U1, U3 is not equals to 0. U2, U3 is equals to 0. So we can conclude that not an orthogonal basis. So we must explain that it is not fulfill the orthogonal set condition, and then we conclude that it is not an orthogonal basis.